Welcome to our session. In this session, we will present our work in building AutoML solutions in a distributed fashion using Ray and Ray on Spark. It is provided as part of the Analytics Zouwu project and has been used by many of our users for their time series analysis applications, such as data center management, manufacturing pipeline maintenance, stock price monitoring, telco network monitoring, and so on. This is the agenda for our talk. We will first give some background of the Analytics Zouwu time series analysis, AutoML, and so on. And after that, we will dive into the details of the scalable AutoML solution we have built, as well as the real-world use cases from our users. First, some background. At Intel, we have been focusing building various technologies to bring AI to big data. We have open sourced BigDL, a distributed deep learning framework for Apache Spark. So with BigDL, our users can write new deep learning applications just as standard Spark programs running on existing big data clusters. On top of those deep learning frameworks like BigDL, TensorFlow, PyTorch, and so on, we also developed an open source project we call Analytics Zouwu, which is supposed to be a higher level data analytics and AI platform, which integrates TensorFlow, PyTorch, Keras, as well as Spark, Flink, Ray, and etc., so that we can provide a end-to-end unified pipeline to our users. So this page gives you a very high-level overview of the Analytics Zouwu stack. As mentioned before, it is built on top of those low-level deep learning frameworks like TensorFlow, PyTorch, and also OpenVINO, as well as those distributed data analytics frameworks like Spark, Flink, and Ray. It can run on your laptop, and then without any code change, it can automatically scale to a large cluster to process your production data. So inside Analytics Zouwu, there is 3 layers. At the bottom layer, there is what we call an integrated analytics and AI pipeline. It is the horizontal layer which allows users to apply those deep learning and AI models to their big data in a distributed fashion. For instance, a lot of our users are running distributed TensorFlow on Spark in Analytics Zouwu so that they can apply standard TensorFlow models to their big data cluster in a distributed fashion, and everything is running inside the Spark across the cluster, processing in-memory data. On top of this pipeline layer, we also provide a automated ML workflow layer so that we can help users automate a lot of the manual tasks in building these end-to-end machine learning applications. AutoML is one of such example, and we will talk more in the following slides. On top of this workflow layer, we also provide a set of built-in models and algorithms for, say, recommendations, time series analysis, and so on. So our users can directly use those models and algorithms in the underlying pipeline and the workflow. Of course, the user can also use any standard TensorFlow or PyTorch model in Analytics Zouwu, and use Analytics Zouwu to transparently scale those deep learning and AI models to their big data cluster. So next, my co-speaker, Shen will talk more details on the time series analysis, the AutoML solution built, as well as the real-world use cases.
So now I'll talk about time series. So what is time series? Basically, a time series is a series of data that is observed sequentially in time. Examples of time series include stock prices, sales volume, CPU I/O monitor metrics, and KPIs in telecom networks. There are several types of time series analysis. Time series forecasting is to use the history to predict the future, and anomaly detection can detect data points which have abnormal temporal patterns. And there are also time series classification and clustering, and so on. One thing to note that it is very common to use forecasting as a pre-step for online anomaly detection. And in that case, we first forecast the future value. And when the actual value comes, we compare the difference between the actual value and the predicted value. If the two values differs too much, the new value would be considered anomaly. And there are also many applications for time series analysis. Demand forecasting can be used for inventory management and resource scheduling. Telecom KPI analysis can be used for network quality management in telecom operators. Sensor readings are also time series, and their analysis can be used in predictive maintenance of high-value equipment. And analysis on service monitoring metrics can be used for intelligent IT operations for clouds. Well, time series forecasting is one type of analysis that we've been dealing with for quite a while. The problem can be defined as, given all history T observations, Y1 to YT, we need to predict the values of the next H steps, that is, YT plus 1 to YT plus H. Although in theory, it is possible to use all the history T observations, normally we only consider the previous K steps, which we often call it the lookback period, as illustrated in the purple area in the right figure. There are various approaches to solve this forecasting problem. Traditional methods such as autoregression, exponential smoothing, and ARIMA are widely used in real-world applications. They're relatively simple, but are not very good at capturing complex temporal dynamics and relationships across a time series. Recently, machine learning and deep learning methods are becoming more and more popular. Unlike traditional methods, which are often informed by domain expertise, new machine learning and deep learning methods are often data-driven. And some deep learning methods, which has been used for sequence modeling, have been applied to time series, such as LSTM and GRU, temporal convolutions, and attention. And there is also evidence that they can outperform traditional methods in several well-known competitions and real-world applications. Although machine learning can do well in forecasting, training a good machine learning model is not an easy job, especially for those who are not so experienced in this field. And that's why AutoML is gaining popularity these days. The purpose of AutoML is to make it easier and more efficient to build machine learning and deep learning applications by automating various stages of the machine learning pipeline. As shown in this figure, stages such as feature generation, model selection, optimization, and evaluation can all be automated by AutoML. Essentially, the task of AutoML is to optimize a target metric within a given budget. Modern approaches perceive this as another optimization problem and uses far more complex methods to solve it than simple grid and random search. AutoML can be used to search for hyperparameters as well as model structures in deep learning. We have chosen Wei-Cheng as a backend to implement our AutoML support in Analytic Zouwu project. Wei-Cheng is a library on Ray for scalable experiment execution and hyperparameter tuning. And Ray is a distributed framework for emergent AI applications open sourced by RiceLab. Ray on Spark is a feature in Analytic Zouwu, which is designed for users to directly run Ray programs on a Spark cluster. So with Ray on Spark, we're able to run our AutoML-enabled time series analysis on Spark cluster without the need to care how to manage the two frameworks. Actually, there's another session dedicated to Ray on Spark in this summit. If you're interested, you can check it out. Okay, so far we have finished all the background part. Now let's come to the core part. Okay, so this is a high-level overview of the time series support in the Analytic Zouwu project. And the time series solution part is highlighted in yellow. At the bottom part, there is a general AutoML framework which provides abstractions of machine learning pipeline stages and automates processes such as feature generation, model selection, and hyperparameter tuning. On top of that, we provide algorithms and models specifically for time series, including forecasting and anomaly detection. And then our users can build their own applications on top of these support for their different usage scenarios. There are three major features in our solution, as shown on the right side. First is that we provide rich algorithms, which include state-of-art neural network models and hybrid models. Second, we provide AutoML support, which automates the training process and saves the tuning efforts. And last, we utilize what's provided in Analytics Zouwu to seamlessly scale the automated training in the big data cluster. Okay, now let's dive in a little bit into the software stack. In the AutoML framework, we can see that there are four major components include. Feature transformer and model are abstractions of the machine learning stages. They can be considered as black boxes, which takes in a hyperparameter configuration to construct the internal pipeline and control the execution process. Specifically, feature transformers can do feature generation, rescaling, and selection, and so on. Models can do a single model training as well as multiple model selection. A search engine is responsible for generating hyperparameter combinations, spawning the trials, and scheduling and keeping track of the trials in a cluster. We have implemented the Raytium search engine to enable search capabilities on top of Raytium. When the search finishes, the results of all trials are retrieved, and the pipeline is constructed from the best hyperparameters and the trained model. The pipeline can be saved to file and restored later for inference and incremental training. And on top of this general AutoML framework, we have implemented some feature transformer and models specifically for time series, and a class called time sequence predictor to enable the automated training flow, and a class named the time sequence pipeline for the pipeline output. Some of the class names may not seem so proper today, due to some legacy reasons, and we're going to change it in the future releases. And you may notice there are two blocks in gray in the AutoML layer. They're in plan but not implemented yet. This is an illustration of the training workflow at runtime. So basically, we use a search engine to drive the entire training process. At the time of construction, the search engine takes in a feature transformer and a model. And it also takes in a search preset to configure how to search the hyperparameters. At runtime, the search engine generates hyperparameter configurations based on the preset, spawn the trials, and schedule the trials on the rate cluster. Each trial runs a different combination of the hyperparameters, and when a trial ends, it will write its results to the HDFS. And finally, after all the trials finish, the results are retrieved from HDFS and analyzed. And then a pipeline is constructed from the best hyperparameter configurations from the results and the trained model, as it is illustrated in the red arrow here. Here's a glimpse of the APIs. To train a pipeline, you first create a time sequence predictor, and then just call fit on it to launch the automated training process. For fit, there is an argument called recipe, which you can use to configure how to do the hyperparameter search. Actually, we have implemented several handy recipes for your convenience, but you can always write your own. And there is also a flag called distributed, which indicate whether this is running on a single node or on a cluster. The result of the fit is a time sequence pipeline, which you can save it to file and load later, and there's APIs for doing that kind of thing. The pipeline also has APIs like evaluate, predict, and fit for evaluation, prediction, and incremental training on new data, respectively. And these interfaces are quite self-explanatory. Okay, last, I would like to introduce a new project, which we built on top of our scalable AutoML time series support in Analytics Zouwu. The name is Project Zouwu. We have created specifically for telco applications. In Project Zouwu, we not only expose the AutoML capabilities for time series in the AutoTS module, we also expose some built-in models without AutoML. And we also provide some reference solutions for typical telecom use cases, such as network traffic forecasting. I'll talk about the details of this reference use case in the next section. Now we come to the last part, the use case sharing and learning. Now, let's first talk about the reference use case in Project Zouwu, that the network traffic KPI forecasting. We know that actually many KPIs are collected from the telecom network, such as download and upload speed, channel utilizations, network traffic, and number of connected users. KPI forecasting has wide applications in telco. A real application that we have worked with our customer is to use KPI forecasting for energy saving. You know that some of the KPIs can indicate the real-time demand. And our customer tries to forecast the KPIs for each cell of the base stations so that they can know which cells are expecting low service demand in the next day. Based on those KPI forecasts, they can schedule shutdown for individual cells so that they can save a dramatic amount of energy without much impact on the customer overall experience. And besides energy saving, people also use traffic KPI forecasting for adaptive network slicing. And that's why we choose KPI forecasting as a reference example in Project Zouwu. And in our reference case, we use a public data set which contains real-world network traffic data maintained by the WIDE project. And we have used the aggregated traffic KPIs, such as total bytes and average rates, as example targets for forecasting. And we use the data in the past week to forecast the traffic in the next 2 hours. We have provided two notebook examples to show how to use Zouwu's APIs to solve this forecasting problem. And one is to use the built-in forecasters, and the other is to use the AutoTS module, which has the AutoML support. This reference case is very close to reality, and some of our customers has built their own application from these reference notebooks, just with slight modifications. Now let's look at the case. This actually is a project that we previously collaborated with SK Telecom. This is another type of application for KPI forecasting. In this case, SK Telecom used the KPI forecast to identify potential anomaly in cells and base stations, and they use them to generate alerts and visualize them in a 3D map. The reason we make an example, such kind of anomaly is very common in telco. Although the case itself is not implemented using the time series solution we talked about in this session, we do have other customers who are using our solution to work on very similar anomaly detection application. SK Telecom has a talk in last year's summit, and you can know more details about this kind of application from that talk. And besides in Project Zouwu, we have a similar forecast model as the one used in this case, and it proved to work better than traditional methods in the real-world customer use cases. Now let's look at a real case which uses our time series solution introduced in this talk. This is a project that we collaborated with Newsoft, which is an IT service provider whose customers include some of the most famous German luxurious automobile manufacturer. And in their intelligent AI ops system, they use forecasting and anomaly detection on monitor metrics for VMs and services. They use the results to generate alerts, help adaptive resource scheduling, and for visualization. In this case, they use our solution with AutoML to achieve the desired forecasting accuracy in a very short time. So now here is a summary of the takeaways from our early users. First, about some highlights. We found that it is an advantage that our models allow extra features beside the target values themselves. For example, we have generated extra time-based features such as peak or off-peak hours, holiday, weekend, and our customers also have their own domain-related features. Such features can significantly improve the forecast accuracy in real applications. And with our provided models and automated training, most of the users can get a satisfactory accuracy faster than their manual tuning. However, not all use cases can achieve a desirable result at a very early stage. And most of the time, it is caused by poor data quality. and missing value plays a major part in it, and the ways to fill the missing value could have huge impact on the accuracy results. Another problem many customer faces is the scale of data. And the problem is often not with the time dimension, but that there are too many time series to forecast. For example, one of our telco customers have hundreds of thousands of cells, and each cell has several KPIs to forecast, which adds up to millions of time series to forecast at a time. And similar thing happens in a VM metrics forecasting in the cloud settings, where you can have millions of containers, and each container may have up to hundreds of metrics to forecast, which would add up to hundreds of millions of time series to forecast. So at such scale, it is clearly not efficient to build one model for each time series. And we have been working on this problem and got some progress. Now, the future work, first, as I just said, we have been working on solving the problem of extremely high dimensional time series forecasting. And we also plan to improve the search algorithm, add the meta-learning and ensemble components. And we're adding more models and features for time series based on customer request. And we are also considering the possibility of adding automatic data preprocessing, which improves the data quality, especially missing value imputation. Okay, so this last page is a big picture of Intel's AI technology scope. You can see that Intel provides a wide variety of hardware, software, and integrated solutions for you to accelerate your data analytics and AI end-to-end. If you're interested in any of these technologies, you can follow the links below to find more details. So now I'm ready to take some questions. If you have any thing that you want to know further, you can ask me now.